Welcome back to my series all about limits. In today's episode, we're going to be looking at what it means for the limit as x approaches a constant of a function to equal a constant. Today's video will incorporate some ideas that have been used in the previous two videos, but I will explain them again in case you haven't seen them. Now, the first thing we want to think about is, what do all these numbers mean? Now, let's look at x approaches c. So we can think about that as x is getting very close to c. Right? X can be a little bit less than c, x can be a little bit greater than c, but x is not necessarily equal to c. So we can describe that more quantitatively by saying that the distance between x and c is small. And we can describe this distance by saying the absolute value of x minus c is small. And there's one more caveat to that, is that x is not necessarily equal to c. So to include that, we want to think about what happens when x is equal to c. Right? We get the absolute value of c minus c, which is 0. So this is not going to be 0. But we also know that this is an absolute value, and we can think about it intuitively, it's a distance. So it's not going to be 0, and it's also not going to be negative. So it's always going to be positive. So we can say that this is greater than 0. The second thing we want to think about is this L, and that relationship between our L and our function. So again, we say that our f of x is going to be closer and closer to our L, right? That's kind of what that limit means, is that we're expecting the value of our function to either be L or to be close to L. And so again, we can think about the distance between f of x and L, and we say that distance is also small. So we say the absolute value of f of x minus L is also small. So if you're looking at this and you're seeing, well, this distance must be greater than 0, but we don't have that restriction on this distance. That's because when we're thinking about what x approaches, we're not thinking about what x equals, right? Not necessarily. So we would like to put this restriction on just to show that we're thinking about x getting closer and closer to c, and kind of that behavior of the function. However, depending on what the function is, f of x might be equal to L in those cases. So we don't need to put this restriction on. Next, we're going to look at a graphical example of a function that exhibits this limit. Now I've chosen an arbitrary value of c and L, and this whole is a little bit of an exaggeration, but just to give the idea that we're not looking at values when x is equal to c, but when x is very close to c. So the first thing we want to do is we want to look at this L and think about values of f of x that are close to L. So let's say we want to look at values of f of x that are within a certain distance of L. So values of f of x are allowed to be within a certain height. So let's say we're thinking about, they're allowed to be within this much of L. So let's call that distance the Greek letter epsilon. So the values of f of x are allowed to be within epsilon of L, or the distance between f of x and L is less than epsilon. And again, if it's going to be less than epsilon, it's going to be less than epsilon above or epsilon below. So we look at this and we say from here, can we choose values of x, right, such that all the values of x that we choose have f of x values that are within this epsilon. So now we want to make some width that we're going to be considering for our function. So we want to choose x values such that within these x values, right, our f of x values will be close to L, and specifically within epsilon. So we think about, well, what are the y values that it can be, right? Our lowest y value is allowed to be here, and our highest y value is allowed to be here. So maybe let's restrict our domain. So we can choose values of x to be within this distance of c. And we can call this horizontal distance delta, another Greek letter. And again, it'll be within delta on both sides, right? Because x can be greater or less than c. So we're saying that our x will be within delta of c. Then our f of x values will have this range. And we see that both of these f of x values are going to be within our epsilon. So we can also think about what happens when we choose a smaller epsilon, right? What happens when we are further restricting the distance that our f of x values are allowed to be from L? So when we further decrease that distance, right? And that's the idea of f of x getting closer and closer to L. Well, it'll be harder, but we'll want to see, can we find some width, some range of x values, such that whenever x is within that range, our f of x values will be within that epsilon of L. So again, we're focused at c, and we want to be within this set of y values. So we're going to want to make a smaller delta than we did last time. So we can make this range of values maybe here. And so you can either go delta to the right of c or delta to the left of c. But the idea is, in both cases, right, you're allowed to go a distance delta of c. So let's see what happens. Our f of x is going to range from here to here. And we see that those two values of f of x are within this width of L. So there we go. We have found a delta such that when x is within that delta of c, then f of x will be within the epsilon of L, right? So what does that mean, right? X being within delta of c. Well, the distance between x and c is always going to be less than delta. So we can write that, right? We can say the absolute value of x minus c is less than delta. And then from there, what happens? Well, the values of f of x will be close to L. The distance between f of x and L are going to be less than epsilon. So we can say the absolute value of f of x minus L is less than epsilon. And so the idea is that for our function to be able to exhibit this limit, what we can always do is we can start with an epsilon, then from there we can choose a delta such that whenever x is within that delta of c, right, the absolute value of x minus c is less than delta. Then we will see that the absolute value of f of x minus L will be less than epsilon. So we have made it to our rigorous definition of this type of limit. So we see that if the limit as x approaches c of f of x equals L, that means that for all positive epsilon, and again, epsilon is a distance, so it makes sense that it would be positive, we can find a positive delta. Delta is also a distance, right? Just in the horizontal direction. Such that whenever 0 is less than the absolute value of x minus c, which is less than delta, the absolute value of f of x minus L is less than epsilon. And again, we can see this with quantifiers. For all epsilon greater than 0, there exists a delta greater than 0, such that for all x, where 0 is less than the absolute value of x minus c, which is less than delta, the absolute value of f of x minus L will be less than epsilon. And like with my other definitions, if you're seeing this and you're saying, Mark, this is a bunch of words I don't understand, we can think about what this would mean. And this goes with the examples that we were doing before. For all positive epsilon, right? So that's just the distance that f of x is allowed to be within L. So for any distance that we're letting f of x be within L, we can always find a positive delta. So that's the distance that x is allowed to be within C, such that whenever x is within delta of C, so we're saying x is going to be close to C, right? So kind of this idea of x approaching C, that f of x minus L is going to be less than epsilon. And so the idea is it doesn't matter how small or how big our epsilon is, it is always possible to find a value of delta such that when x is within that delta of C, so we're only letting x be certain values, that the distance between f of x and L is also going to be less than epsilon. So there's one more thing that I want to talk about before we finish this video. And this is the fact that sometimes this limit is going to be very easy to compute, right? Sometimes you'll just be able to look on a graph and you'll just know what the limit is. And the reason that we can justify that is because of something called continuity. So continuity is easy to think of intuitively, right? We can look at a graph and say, is that graph continuous? Is that graph not continuous? Is it continuous at certain points? And the way we define what continuity is by saying the limit as x approaches C of f of x is equal to f of C. So this is what it means for a function to be continuous at a point, right? Is to say that the values of f of x, when x is close to C, right, would lead us to believe what the value of f of x is to be at C ends up being the same thing as f of C. So if you go in and you know that a function is continuous, finding this limit is computationally the same thing as finding what f of C is. And that's what's so special about continuity. So again, we go back and look at our definitions. And we see that it equals f of C. So the distance between f of x and f of C, and we can change it here as well, right, will be less than epsilon, right? And what's special about continuity is that when you actually get to x equals C, then obviously by the definition of a function, f of x will equal f of C when x equals C. So that's the idea behind this type of limit and behind continuity. Thank you very much for watching.